So good night, everyone. Welcome to the third AstroCamp public talk. So tonight you'll be hearing about statistical methods in astrophysics. So the goal of this talk, what I want you to take away, is not to be able to be to apply any of these methods or to become an expert on statistical methods in astrophysics, but just to know that what is available, what tools you use, and to have a bit of understanding of how this works. And at the end, we'll be able to see some examples of applications for what I find interesting cases, other than astrophysics, of course. So let's start just giving a motivation. So astrophysicists want, among other things, to study the origin and evolution of the universe. And for that, we need theoretical models. Okay, so we want to describe the dynamics and evolution of the universe. We need to have some model that tells us how this happens. And the model we currently have and currently accept is lambda CDM. So this equation here, you're already familiar, at least this type of equations, Friedman equation. So you can see the Hubble parameter and Hubble constant, the scale factor, but you might not be familiar with those other terms. So this is the Greek letter omega, and this just tells you the fraction of the constituent of the universe. So this is the omega matter, omega radiation, and omega lambda. So basically, they just tell you the fraction, the amount of matter, radiation, or cosmological constant you have in your universe. And because you want to account for everything in the universe, these three quantities will add up to 1. So they're just smaller than 1. So for example, we take this to be 0.3. But as already has been spoiled there, we have some problems with this model. I'm just going to name you a few. So one of them is H0 tension. So what is that? So basically, we have several ways of measuring H0, this Hubble parameter, and they are in tension with one another. So what does that mean? They do not agree. You use some methods to calculate its value, and they do not agree. They are incompatible. And well, there are several ways of trying to explain it or try to go about to solve the problem. And one of them is to explore other models other than lambda CDM. So that's the main thing about H0 tension. Another thing is cosmological constant, which I guess you're familiar now, but I'll recap anyway. So basically, this cosmological constant can be computed by particle physicists or by cosmologists. And when they do it, they do not agree with each other. So they actually find that the value disagrees by quite a lot. And that is one problem we encounter. And then finally, cosmological lithium. So our theoretical models basically tell us that you should have some abundance of lithium that you should measure, and basically what you measure does not agree with it. So basically, we have some problems with this model, and we want to go beyond. One way of solving some of these problems is to look at other models. But you might wonder, how can statistics help in astrophysics? So for example, we might be interested in testing a hypothesis. For example, you might wonder, oh, is the universe homogeneous? Is the universe isotropic? If you're curious enough, you learn some statistical methods and you can apply. You have to take averages of quantities, and you can try and falsify or verify this hypothesis. You can also use it for parameter estimation. So you already know what means this parameter, just a fraction of matter we have in our universe. And you might be studying a certain model that describes the universe. And you can use statistical methods to actually calculate in the context of that model, what is the most likely value for that parameter with associated uncertainties. Model comparison as well. So you might be studying not one model, but 2 or 3 models, and you have sets of data that you use, and you might wonder, okay, I have this data, I have these models, but which model fits my data better? So you might expect that one model might be slightly better or might explain data better, and you want to figure out why. You can not just look at it and say, oh, this one is better. No, you need to do something, and there are statistical methods to do this. And finally, forecasts. So you might want to, help improve the design of a future experiment. And for that, you can use forecasts, which is some statistical methods that predict the performance of future experiments. And then you can have a better idea, and you can help, engineers or whatever, people who are building the experiment to, help improve its design. But now we can come up to something a little bit technical, and I would like to introduce you to the Bayes theorem. It's just a statistical theorem of statistics, a very fundamental one. And I'll explain everything that's here. I'm just introducing to the names. Okay, so we have the prior. So it's a probability of H. H is our hypothesis we're testing. So it might be a model, might be whatever you want. And then we have the likelihood, which depends on the hypothesis and on the data available to us. We have the evidence, and then the quantity we're calculating, which is the posterior. Okay. So like I said, we have the prior, and what is that? So basically the prior is our hint or our intuition, our initial guess for what is the outcome of the probability distribution before you do any analysis, before you start anything. So you say, okay, I think it's going to be something like this, and that's your prior. Then we have our likelihood. So likelihood is the probability of the data given the hypothesis. So you have your hypothesis, and the likelihood tells you how probable is for you to measure the data that you have. Then you have the evidence, the probability of generating the observed sample from a prior. And like I told you, the quantity that we're interested in calculating is the posterior, which is basically the probability of given a certain data for you to have your hypothesis. And you can understand how this is like the interesting quantity, because you don't start from likelihood, you start from a prior. So you start from having some data, and you want to know, okay, how probable is my hypothesis? Okay, and how can we apply this? So basically, it's like a cooking recipe. You just pick your favorite model, and then you apply Bayes' theorem, you get your posterior probability, and then you get your most likely value of parameters with uncertainties associated. Okay, so this is just a small flavor of Bayes' theorem. But what I really want to get into is something a little bit more sophisticated, and that I use quite a bit. And that is Markov chain Monte Carlo, or MCMC. So it's basically just a very efficient way to estimate parameters and uncertainties. But you might wonder, how does it work? I mean, it's just a fancy name. Okay, so I'll split this into 2 bits, and then at the end, I'll put them together. So we'll start with Monte Carlo sampling, and then Markov chain. Okay. Monte Carlo sampling is basically just a technique to generate random numbers. Okay, but it's not that simple. So basically, I can tell you, okay, pick a random number, or I can have something that gives me a random number from 0 to 5. But that will have a equal probability of you getting 0 or getting 5 or getting 1. But that's not very useful, right? I mean, in the stuff we used to, or we want to calculate, not everything has the same probability of happening. So basically we use probability distributions that just give you the probability of occurrence of a certain outcome for an experiment. So Monte Carlo sampling just basically gives you a random number, but not, or a random input, whatever it is, but with the caveat that not all inputs are equally likely. Some are more likely to come out than others. That's just basically it. And then Markov chains. Okay, so we have our random number that's been taken from a probability distribution, like I told you. And now this is just a way of linking those inputs. But they get linked in a way that's also specific. So your past events do not affect your future events. And it will become clear in a bit. And we'll talk about conditional probabilities. It'll be useful for us. Okay, so on the left-hand side, we'll just have usual random selection. So let's say we have a box with balls. So we have 3 blue ones, 2 pink or red ones, and 2 green. So in a random selection event, let's say I don't look, I shuffle them, then I take one, and I take a green one. Okay, so what happens in the box? There's 1 green less, right? We just have 1 green one. So then imagine I take again, and I take another green one. So in all the future sequence of events, I cannot take any more green balls, right? Because there are no more. Okay, so that's the difference in Markov chains. Markov chains don't care about that. They just keep coming. They just replace the ball. So I take green one, they put the green one. I take a red one, they put the red one. So that's what I mean when I say that future events don't get influenced by past events, because you always get a reposition of your states. Okay. There is another caveat. So this is the way. So the reposition, I think you understood. But we will have to do something else to the events. So we'll have either to accept them or to reject them. And for that, we'll use conditional probabilities, like I told you before. So the future events are not affected by your current event. So let's say I take a green ball. So the next ball I take does not get affected because of me taking a blue or a red or whatever. But the fact that it gets accepted or rejected does. And that's because we need some way of sorting. We don't want every state to get accepted, but we want to influence the way it gets accepted using a probability distribution. So we want to try and accept the good states and reject the bad ones. Okay, so just before I put the two things together, so Monte Carlo sampling generates random numbers, like I told you before, with a probability distribution, and Markov chain links those events. Okay. So now, okay, we'll go through this by phases. So let's say we have a state A. Okay, it's our state, has been accepted, and we start from that point. We have Monte Carlo sampling, and we generate a random state B. So now, like I told you before, we either accept it or reject it. And for that, we do a coin flip, but it's a special coin. So, you know, coins have 50-50% odds of having tails or heads, but now you have the probability distribution. So not all, so it's like you have more probability of having tails or heads or whatever. So you get accepted if you do that special coin flip and you use that conditional probability. So you have the probability of having the state B if you have the state A before. So let's say you get rejected, you do the special coin flip, it lands on tails. Oh, you reject the point. Okay, you reject the state. That's the end of it. So you go back to phase one, random state, you get a new state, and then you do the same thing. Okay, get accepted. Gets accepted, you just start the game again. So you get your state B, and now your state B is the new state. You generate the random state C, and then the same thing again. Okay, and then you do this many times, so that you have states that cover all the region of your. So in cosmology, you normally do this for parameters. So you cover all the parameter space, and you get states because we use probability distribution. So we use something that tells us, okay, this is the most probable state, or this state we accepted it, but it's not so probable. So you get density of states around the most likely value, and values that are not so likely. You might get some states accepted because this is random, right? This is random stuff. So it can happen that you get a state that is not, you know, so close to the most likely value, but it will still get accepted, but it will get accepted not so often. Okay, so you get dense regions around of states around the most likely value. Okay, so was that clear? Yeah, okay. So now, okay, this is all very theoretical, but I mean, what what can this be used for? And I'll just give you a couple of examples. So for example, in engineering, so let's say you're building a wind farm and you want to know if it's going to, be profitable or not. You can actually use MCMC methods to predict the output, energy output of a wind farm during its lifetime. Also for computational biology, so let's say you're studying a certain molecule and the molecule lives in a certain environment surrounded by molecules or whatever. And you can use those methods to predict some, reactions and chemical reactions, chains of reactions that can happen for that molecule. In finance methods, so you can evaluate risk of certain investments using these methods, which is quite useful. I mean, you don't want to lose money. For rescue operations, so let's say, actually, the USA Navy uses these actual MCMC methods, so to predict the location of vessels. So let's say you have a lost vessel somewhere in the sea, and they can make their search operation and rescue operation more efficient by using these methods to locate the said vehicles. For computer graphics, so you can make graphics better and better by using MCMC methods. So basically just trace all the possible directions of light rays using these methods, and you can actually improve graphics. And AI for games. So basically, most AI programs that calculate for you the best possible moves some of them actually use MCMC methods. So basically, they say, try a possible move, and then the MCMC chain, the thing I explained to you before, does this process and tries every possible response from the other player. And doing that, you can search actually the best possible move for that. This game, just a curiosity, I think it's very cool. It's called Go. It has a 19 by 19 square matrix, and it actually has more legal moves than atoms in the entire observable universe, which I think it's very, very cool. And finally, I want to talk, even though this is very cool, I want to talk about personally what I think it's the most cool application, which is my work. Okay, so basically I work in this fancy name, Generalized Bekenstein Model, which is basically, like I told you in the beginning, a model that goes beyond the standard model. So I told you in the beginning, the standard model has some problems. Okay, we're searching for models that go beyond. So what we do in simple terms is we add additional degrees of freedom. So we let the theory vary in different ways. So we introduce scalar fields. Okay, it's just a fancy name to say that we let it have additional degrees of freedom. And that has some consequences. So for example, we can have alternative descriptions of dark energy. So dark energy is described by a constant in lambda CDM. And some of these models that have this feature can have dark energy that varies, that varies, is not a constant. And what I mostly work on is on the right hand side is consistent theories of variable fundamental constants. So when you add additional degrees of freedom, you can have theories of what I work on is variation of alpha, the fine structure constant. So I think you talked about it in CARLO's class, but just basically a quantity that quantifies the strength of electromagnetic interactions. Okay, so I showed you this for lambda CDM, and now this is for this generalized Bekenstein model. Okay, so this scale factor the omegas, you already know what they are, but I'll just tell you to what quantities they represent. So the B's stands for baryons. So baryons are basically just ordinary matter. You are made of baryons, I'm made of baryons. And then the chi's, we are not made of those. Those are just dark matter. So we use a candidate of dark matter. I hope you're not made of those. And then the last one, is just cosmological constant. And then the only thing is these Greek letters, not an N, is an eta. And it's basically just a coupling, just tells us how does that degree of freedom, how strongly it couples to that quantity. So let's say that eta B tells you how strongly it couples to baryons, to ordinary matter. And like I promised, we have variation of fine, sorry for the bright lights, it has variation of fine structure constant. So this is, okay, just some equations, but just to tell you that you can actually have a variation of alpha. And if this were not to be true, so if we were in lambda CDM, we would just see a straight line. But because we're not, so we have this, we see this baryon function. So we have these three lines, it's just basically different values of the parameters I told you, these etas, okay? Okay, so I just want you to notice like the order of magnitude is small. It's small changes, otherwise it wouldn't be good for us. Okay. Now I just want you to have like a sort of an idea of how we constrain these models, like what data we use. And I don't want to get into too much detail, but basically to constrain variations of alpha, we use spectra from quasars. I don't know if you know what they are, if you heard. It's just quasi-stellar objects. So they are very, very bright objects in the center of galaxies. Okay. And then I would just want to tell you about another way of constraining the parameters of, the parameters of this model. And I think you learn about this today, but I'll talk about it. Sorry. So the equivalence principle basically just tells us that two different bodies of different compositions fall at the same rate in a gravitational field. And you can see from the equation on the right, so eta, and I apologize for the bad notation, is not the same eta as the parameters, is an eta that quantifies the equivalence principle. And if you see on the numerator, you have 1 is your body 1, 2 is your body 2, different bodies, different compositions. And if equivalence principle holds, they experience the same acceleration in a gravitational field. So A1 is the same as A2, so the numerator is 0, and eta, that quantifies the equivalence principle, or the violation, I should say, is just 0. But if it's violated, two bodies of different compositions will accelerate at different rates. And then you have an eta that is not 0. So why is this? I mean, we're talking about, we're talking about alpha. So why is this useful for us? Actually, it happens that when you have a theory that has variation of fine structure constant, the alpha, you actually get for free violation of equivalence principle. And I don't know if you wondered, why is this picture here? So this is an experiment called microscope that basically just measures this violation. So basically you have this satellite in orbit, and you have two different bodies, I think it's platinum and titanium, that are in constant free fall, and you just measure tiny differences in the acceleration of those bodies. And you can see that now. So basically on top is just eta for our model, and it depends on the etas that are the parameters. I'm sorry again. Okay, and you can see that the constraint that this model, so the data that the experiment gives us is very, very small. Okay, so this is actually a very good constraint for us for many reasons. But it's a very good constraint for us. And so just before I show you the results of this work, so I told you we have the parameters we want to constrain is coupling to baryons, dark matter, and cosmological constant. But I will just show you the constraints to matter, in which you combine baryons and dark matter, and cosmological constant. This is more a technical issue, why we don't constrain both separately, but okay, it's not very relevant. So basically what we do is we use MCMC method. So we have the equations that describe the evolution of the universe and of the scalar field I told you about in this model. And we use MCMC methods to sample throughout the parameter space. Okay, so we do those steps that we told you about, Monte Carlo sampling and Markov chains, to actually find the most likely value with uncertainties associated. And here you see just counter plots. So here you can actually see what I was telling you about. So you sample throughout the parameter space, and you get, you know, when it's darker, it has more points, more accepted states. And when it's lighter, it has less accepted states. So there you can see the most likely value is around here for lambda and m, so it's around here. And you can see you still get accepted here, but it's much lighter, which means it's less dense in states. So you can still get accepted, I mean, a bit far from the region where you actually have your most likely value, but when where it's denser is actually very close to the accepted value, which the most likely value, sorry, which is this one. Okay. Okay, so that was it from me. Thank you very much. Don't know if you have any questions.